Hello, and welcome to the second video in my series on plotting and visualizing data using the Julia programming language and Plots.jl. In the previous video, we learned the basic functionality of the plot function from Plots.jl and learned how to plot series data, where we had an array of X values and a corresponding array of Y values. From this data, we were able to plot line charts shown here. And then we also learned how to customize our charts to appear in a certain theme, to give the charts titles, to label the X and Y axis, and to also have an appropriate legend appear. In this video, we're going to continue our study of the Plots.jl package, but in a different context, in a context that I think a lot of instructors will like. And by that, I mean, we're going to look at plotting mathematical functions that are built into base Julia. Now, base Julia has a ton of built-in functions. So all of this, the trig functions, we have exponential functions of different bases, we have logarithmic functions, and hyperbolic trig functions. So these functions appear a lot in courses like calculus or pre-cal. So I use Julia, well, I used to, and I plan on using it this semester when I teach Cal 1, I use Julia to pull up quick charts, quick plots of function behavior on these given functions. So we already know how to make line charts with series data. So it's just as easy for making line charts of these mathematical functions. In fact, it's probably easier. All we need to do is type plot, and then give the plot function what's called an anonymous function, a one-line definition of a function. X goes to, for this example, I'll say sine X. And again, sine X is built in. If I come down here to the REPL and I type sine of pi, I see that I get some basically zero value, right? So just got to save this script and run it, or which I didn't do last time, you can just highlight your lines of code and press Shift Enter, and I see that my plot appears over here, but it's small. This has been happening with me in VS Code because I keep on switching between different scalings on my monitors. I have several different monitors in my house, and I'm always moving from one to the other, and my scaling is just all screwed up here. So what I'm going to do in this first plot here is I'm going to set my DPI equal to something like maybe 350, I think would be appropriate. This should rescale and make the scaling appear much better on my monitor. You might not even have to type DPI, but just know that that's a way to fix the sizing if you encounter this problem using VS Code. If you're in a Jupyter notebook, you won't have to worry about this at all. If you're in a Pluto notebook, you won't have to worry about this at all. So back to what this lesson is about, plotting mathematical functions. Look how easy this is. I just had to pass in a function, and I gave the sine function, and it showed up. Now, it's kind of strange, though, especially if you're coming from like a Python background with matplotlib, where you have to give series data in a sense. With Julia, though, and the Plots.jl package, it will automatically generate the charts for you. It will find some domain to pass into your function, and that'll just be what it uses. So for example, if I change sine to cosine, and I just ran this, then I would see that it changed to the cosine function, right? So it just does this for us, which is really, really convenient when teaching, right? The quicker that I can do this in class, the better, okay? But this type of plot is not too convenient yet, because when I'm typically talking of the sine function, or when I'm teaching the sine function to my students, I like to restrict my intervals. Currently, this interval -5, 5 on the x-axis seems somewhat arbitrary. However, Plots.jl makes it really easy to set a specific x interval for this sine function to be plotted on. And that's as simple as typing xlim and then giving it a tuple of left value and right value. So your starting x value and your ending x value. So for the sine function, I probably want to start at 0, and maybe I want to end at 2 pi. So 2 times backslash pi, press tab, 2 pi. And this is built into Julia, super mathematical. So now, if I highlight these lines of code, press shift enter, I see that the sine function is now doing the behavior that it should. Sine of 0 is 0. Well, where's pi over 2? Sine of pi over 2 is 1, so I can't see that too clearly. So this is another thing that we need to fix. We need to label the ticks, the marks on our x-axis, to be more descriptive of what's going on, especially if we're teaching this to students or describing it to colleagues. The way that we can do this is by specifying what the x ticks are going to be. Okay. Now, the way that we're going to do this is with the x ticks argument, and we're going to pass this a tuple. Okay. Now, the first entry of this tuple is itself a range of x values. So I'm going to use the step range type and start at 0, colon. I want to take steps of pi over 2, colon, and I want to end at 2 pi. Okay, so here I have specified the x values that I want to appear down here, right? Now, if I don't put anything in the second entry, let's see if this actually runs. I'm curious. There's a problem. Maybe if I get rid of this, I want to see what happens. I'm just playing right now because that's what I like to do. So what happened? Oh, I'm missing a comma too. Okay, so let's see if this runs. Okay, so now I see that it did run. Ignore these errors down here. I see this is 0, pi over 2, 0, pi over 2, pi, 3 pi over 2, 2 pi. But these floating point approximations to those values are not very descriptive. So if you would like to be more descriptive and give strings to represent these values to make a prettier looking plot like you might see in a textbook, you can pass in a tuple where the first entry will be your set of x values, and your next entry is an array of the strings that you want to correspond to each of these ticks. So for example, if I put in 0 right there for my first tick, and then I put pi over 2, my second tick. All right, so let's see what happens. There are 1, 2, 3, 4, 5 ticks, but I only gave it 2 strings to look at. So what's going to happen here? Shift enter. Oh, it only labeled the first 2 ticks. So if I want to label the rest of them, I just have to fill them out. So what's next? We have pi, and then we have 3 pi. Remember, these have to be strings. 3 pi. Oh, I made a mistake there when I got rid of the string. There we go. 3 pi over 2. And then finally, the last entry should be 2 pi, like that. Okay, everything looks good. So now if I run all of this, I have a nice looking intervals on my x-axis, which is really cool. I now see that this is sine of pi over 2. This is sine of pi is 0. Sine of 3 pi over 2 is -1. Sine of 2 pi is 0. Informative. However, the font looks a little small, so I can adjust that with the keyword argument. So this is going to be tick font size, and maybe I'll set this. I think it's by default set to 3. I'm going to see what happens if, oh no, default set to 8. So let's see what happens if I set the tick font size to be 10. Did it do anything? Maybe 15. Maybe my DPI is messing things up. Let's run this again. Oh, did I? Oh, it's because I didn't say it, type it right. Tick font size, typo, annoying. All right, so now we have these big ticks, probably too big. I should have left it at 10 because I'm almost positive the default is 8. All right, so now we have nice looking tick markers here, and it looks good. Now, I sort of want to give myself a little bit more leeway on the y-axis. It's kind of getting squished up here. So I can set what my y limbs are in a similar fashion to the x limbs. So y limb is going to be a tuple, and then I'll say like maybe negative 0.5 to 1.5 or something like that. Be sure to put your comma in there and then run that. Oh, too big. 1.05 and then 0.05. Let's try that out. See what happens. Too far down. Trying to adjust these things as we're going. Why is that messing it up? I'm curious. I hope I'm not doing some silly mistake. Oh, it's not 0. What am I doing? That was a silly mistake. I need to go negative 1.05. I apologize for that. So now hopefully this will look. So yeah, now I have a little bit of space above and below my graph. Maybe I want to make it a little bit further like this. So we'll just run that. All right, so now I see I have some space to work with. What else do I need to change? Oh, the legend label. So I need to give it a label now, which is a string. So sign of X. You should put that comma there. And then this should be about as fancy as we want to do it. Nice. And again, if this is too dark for you, you can change your theme. I have my theme right now set to the dark theme, but if you wanted to, you could do, for example, ggplot2 like that. And then now there should be like a gray hue in the background. Okay, so maybe I'll stick to, well, no, I like the dark one. I'll stick to the dark one. If you would prefer the lighter one, please comment down in the comments below. I'm still learning how to present this content to you. I'm used to teaching in person. Teaching online, it's a new thing for me, even though I've been doing it since COVID, but I still am learning. So please let me know any suggestions you have down below. I'm more than happy to listen and to learn from you guys. Okay, and so hopefully the next time I make a video, it will be better. Okay, so maybe, what did we learn last time? Line width. We can change the line width. If you watched my first video in this series, line width, okay. 8, I don't know. Let's see what happens if I just run that now. Oh, that's a little too fat for my liking. Maybe 3. Let's see. All right. And then, as you know, one of my favorite colors to plot with is magenta. So I can do a line, just color equal, give it the symbol magenta. Put that comma in there, run it. All right, and then we have a nice looking sign plot here, okay? Now, I don't think I want to mess with the line width, actually. I like the width of the original line that I had. Okay, so now suppose we want to overlay the cosine function on top of this function. Well, if you watched the previous video, you'll know that the convention in Julia is to use the exclamation mark when we're using a function that's modifying the current object that we have. So with this plot function, we made this figure. And with the next plot function with an exclamation mark, we're going to modify this figure by adding in another plot. In this case, I'm going to look at cosine, and I'm going to pass that in as that anonymous function. So let's just see what happens if I run this code here. So now we see that cosine has been defined here, right? Now, again, we can customize it as we did the sine. So we can say label is equal to cosine of x. And then we can also say something like the color. My second favorite color is light sea green. Okay. And then maybe that's all I want to change. All right, that looks kind of nice. I'm pretty happy with that. So far so good. This is looking good. Now, what else can we do? Well, maybe instead of overlaying these plots, maybe we want to make two different figures and visualize that at the same time. Well, the way that we can do this is by defining the first plot to be a variable, call it P1, okay? Now I can remove my DPI here. I think it's already been set. Once you set that once, unless you change it again, it should stay the same. And then with this second plot function, I need to give it another, I need to assign that to a variable. So in this case, plot2, okay? So now, if I'm doing this, I need to get rid of that exclamation mark to indicate that this is a completely separate plot. With that being said, since I'm no longer overlaying onto this figure, I need to add all of this business here that's labeling up my figure. So I'm just going to go ahead and copy that, come down here, and then paste it. So just skip that over like that. I like lining up all my code as cleanly as possible. So everything seems to be matching as far as labeling goes. Okay, so now that we have these variables, we can plot them one at a time if we want, right? So if I come down here and I say plot P1, right? Oh. If I come down here and say plot P1 and save it and then run, let's see what happens. Oh, the DPI did change. Okay, so inside of this plot function, we just specify DPI. I think it was set at 350. I already forgot the DPI I had. Okay, 350. All right, but if I want to plot P2, I'll just pass P2 in there and then run it. Okay, so now what if I want to plot both of them? Well, I can pass into the plot function P1, comma P2, and then give it a keyword argument layout equal to 1 by 1. Or no, 1 by 2. Let's try that. Save that, and let's see what this does. So what has happened here? Well, we pass into the plot function the sine plot, which was stored as the variable P1, the cosine figure, which was stored at the variable P2, and we specified that the layout is 1 by 2. So the tuple that you pass into this argument here, this keyword argument layout, is specifying the structure of the super figure that you're making here. So notice that there's 1 row, 2 columns of figures. That's what this layout is specifying. If I changed it up and I did 2, 1 like that, then what do you guess is going to happen? Let's see. Now we get 2 rows, 1 column. Okay, so this is really easy to do. I know Matplotlib is awesome. I love Matplotlib. I love Python, but I do think that this is easier for stacking plots on each other. It just seems so natural to me. Okay, so that's really cool. And I hope that you experiment with this and maybe try plotting other things. So for example, well, I'll get to that later. Let's focus in on these two functions here, sine and cosine, stored as P1 and P2 plots. Those variables are storing their plots respectively. So I'm going to go ahead and focus in on sine. And remember, because my screen size is changing all the time, I need to set my DPI. You probably don't have to do that. So we're just focusing in on the sine function. What if I wanted to somehow like annotate this this graph here. So for example, when I teach Calculus 1 this semester, we're going to spend a lot of time on optimization and looking at critical points and extreme points or extreme values, i.e. local minimums, local maximums, global maximums, global minimums. These are very important concepts, especially in machine learning. So what if I wanted to somehow annotate where these critical values are, where these extrema are? Well, I have just plotted a figure, this one. So there is a function called annotate. And I'm modifying the current figure so it's convention to give the exclamation mark. And it won't work if you don't give it the exclamation mark in this case. Now, what we pass into this function is going to be an array. And inside of this array are going to be tuples that represent where and what you want to annotate onto the figure. And I think the best way to describe this is with an example. So I see here that we have a local, it's actually a global maximum, but it's an extreme value right here. This is a critical value. The derivative of the function is 0 right here. And that occurs at x value pi over 2 and then y value 1. So if I want to annotate just above that value right there, I need to pick a point above it. So for example, the x value will be pi over 2, and the y value will be, let's say 1.2. I know that I gave myself a little bit of room. The top is at 1.10, so 1.2 is like right there. Okay, so that's the second value that I give it. And then, actually, I should have said this is a triple, not a tuple. The third value I give it is what I'm going to annotate it with. So this will be another tuple that's going to give the keywords, or not the keywords, but the annotation itself. So I can say extreme, I'll say maybe local maximum. Okay, so that's what I want the string to say. I want it to have a font size of size 12, maybe. I want to color it gold, maybe. We'll see what that looks like. And I want to center it. Okay. So that closes off my tuple there. I'm missing, where is it? There it goes. Okay. So I have my x value, my y value. That's the location of the annotation. And then the text, the size of the text, the color, and the positioning. Okay. All right, so let's run it. Let's see what happens. It's too high. I can barely see it up there. I need to give myself more room. So maybe I need to bring it down a little bit, like that. Save it like that. Maybe that was too far down. 1 point. So that's like how high it is, and I can barely read it. So I'm going to make this blue. Save that, run it. Nice. It's starting to look a little bit better. My font looks a little bit big. Maybe I'll do it 10. Run it again. Nice. There's my local maximum. And what if I wanted to actually plot the point that occurs there? Well, we haven't talked about scattering yet, but I'll go ahead and do it just to illustrate a nice looking figure in front of you. So I'm going to now scatter with an exclamation mark. Scatter is meant for discrete plots, not these continuous looking lines. And what we need to pass into it is an x value and a y value, both in arrays. So you scatter series data, so x arrays and y arrays. In this case, we were just going to scatter a single point, so 1x, 1y. We can scatter by doing, so the x value is just pi over 2. That's my first array. And then the second one I know is going to be 1. And then I'll give this a color red or something like that. Oh, okay, so let's hope, I hope this works. Let's see. There it is right there. I'll give it a label too. Save it, run it. And then I see I have a nice looking extrema point with a label right above it. And maybe I'll make it like a little bit higher up like that. Make the font a little bit lower. Save it like that. Execute it. Nice. That looks really cool. Right? It was really simple for me to do that. As long as you know that annotations are just X and Y values, and then you can pass it the text you want to annotate it with, the size, the color, and the location. Now, this is one way of doing it. I'll show you in other videos as this series continues, kind of doing it step by step by calling annotate over and over again. And trust me, it's a very simple concept, and it's much easier than other plotting packages I've seen in Python. Not that I have anything against Python. Again, I love Python, but this just seems to me very easy. So now that we know to do this, we should be able to do this for this local min over here. Like literally, I can just like copy this right here, come down, paste it. I know that this value here occurs at 3 pi over 2. And I want to put this at -1.07. So like down here, local minimum. That'll be the text. And then here, I just need to change this to 3 pi over 2, -1, color it red, extrema again, and then save it and run it. I think that should work. There it goes. Awesome. That is just amazing. Amazingly easy. Okay. Now, hopefully this gives you an idea of how to plot these functions. And I encourage you to watch this video and then go on to the Julia documentation and look at the other mathematics functions that are in base Julia. There'll be a link down below. And to play around with making your own nice looking figures, right? So for example, I know that there are exponential functions and logarithmic functions. I can get rid of this figure here by just typing plot x2 log base 2, maybe x like that, give it a label equal to log. Oh yeah, that's how you do it. \__tab 2 \__ there of x, like that. And then I should see that up here. Almost forgot my dang DPI. I really am annoyed by that. I've learned how to deal with it, but I hope that you guys don't have to deal with setting your DPI because you're not going back and forth between different monitor sizes and resolutions all the time. Let's take a look at this log function, log base 2, there you go. All right. Thank you for watching. If you've enjoyed it, please like and subscribe down below. Also, please give me comments. I check my YouTube feed pretty much every day, and I want to hear back from you guys so that I make better and better videos. I'm slowly learning, and I hope that I'm getting better, but still, the more I hear from you, the better I'll get. Thank you for watching, and I will see you next time.